do you work with limits when you're dealing with multivariable functions? And we've seen a little bit of this before with vector valued functions, and the idea is going to be pretty close to the same thing. But the difference between what we talked about before and now, with a vector valued function, we're just following some path through space. It's not a surface. It's just like a yarn string loop through space there. Now we're talking about our surfaces. So we have some kind of actual, shape to this thing that we'll be working with there. So we're still talking about finding limits and things like that. A lot of similarities will be a little bit different there. Okay. So if we think back to Calc 1 stuff, and I draw a lot of parallels in this section between Calc 1 and then what we're doing now. This is just taken from the book in Calc 1. In Calc 1, we kind of give this arbitrary definition for what a limit is. And we say that as our x values get closer and closer to c, our y values get closer and closer to L. And that's our kind of basic definition. Let me go through and work on some more here. So for a multivariable case, we have to expand that a little bit because we're not just approaching one point L, we're going to be, or one point C, we're going to be approaching like a point in an x direction and a y direction. So more of like a disk that we're working with there. But we're going to spend just a minute here. So drawing on this picture a little bit here, hopefully we recall if we've got just our good old x and y, and we've got some function. Who knows what it is there? We've got some function. The idea is that as x gets closer and closer to these values of c, so as we approach it from the right, as we approach it from the left, on that function, what we should be getting to is that point L. And if you remember epsilon delta limits, we'll talk about those a little bit more in a minute too. They relate back to this also. And I'll pull up the Desmos thing in just a second for that. But the question is now, okay, well, now if we have x and y, and this picture is like our domain, we need a way to express this in terms of a new output variable, which is going to be z there. And so if we try to draw a similar picture in a three-dimensional case here, we've got our x-axis down here. We can have our y-axis over here. And then our z-axis goes straight up. And then instead of just approaching some point C, we're approaching some point, and our book calls it x0, y0. So we'll stick with the same notation. So just draw some random point out here. It doesn't really matter too much where it is. There we go. So this is the point that we're approaching now. Since we are approaching this one dot, we're not just coming at it from the left or the right, but there's an infinite amount of directions we can approach this point from. Anywhere around the circle we can approach it in that direction from. And so what we're going to talk about, instead of just approaching C from the left or right, is we're going to talk about approaching this point from like a circle, which is called like a delta neighborhood. So you can imagine you just have like a little disk around this shape, and that's kind of where we're approaching this point from. Anywhere in that disk, we're getting closer and closer and closer to this point, this x0, y0 point, right? And then on our surface, we have some kind of surface here. I don't know how well I'm drawing this, but let's say we've got some kind of three-dimensional surface. Okay, and if we were to trace this point up, it does hit somewhere on that surface. Okay, and that's our z component, and we can still call that L. We can still go back and say, okay, well, that hit somewhere on the z-axis at L. Okay, so we won't change that notation too much then. Make that a little clearer. All right, so really we're just saying, okay, well, instead of just approaching a point from the left to the right, I'm still approaching a point from this whole disk around. And so we're going to have this little neighborhood, this delta neighborhood of values that we're going to get close to instead of just the left and the right that we have to go through and check here. In terms of showing limits, it's going to be pretty much the same thing we did before, direct substitution. If you can just plug in the values that you're trying to approach and find the limit, you're done. Really, we're only going to have problems when we have indeterminate form where if you plug in the values, you get like 0 over 0 or something like that. But we have the same ways we're going to go back and fix those. Or if the limit doesn't exist, we have to have a different way of going through and showing that. And we'll see an example of that in just a minute here too. But it does make things a little more complicated, although it's pretty similar to what we've done before. Okay. So before we get to those examples, though, a little more on these delta neighborhoods of these circles here. We do want a way to kind of describe this little blue circle we had drawing out previously over here. So like, what is the equation for this circle here? So whether using your knowledge of distance or circles or Pythagorean theorem, because they're all related, here's how we can go back and write that little disk right here. So this thing there is how we can represent this in the equation. And that should look pretty similar. We've got x minus x0 squared plus y minus y0 squared, kind of your basis for a circle in 2 dimensions. And then take the square root of all of it since we've solved it for that radius. Since we are saying less than, we're talking about everything inside of this circle. Okay, and the center of this circle is that point that we're approaching. That x0, y0 is the center of that circle. Okay. Does that kind of make a little bit of sense?
Yeah.
We'll have to do nods. Okay, thumbs up works here. Okay. So this is the region we're going to be working in. So when we usually talk about approaching C from left and right, and we do talk about our epsilon delta proofs there, we have to set values for delta and set values for epsilon. And we're going to work through one example like that too in just a minute. But what we're going to be looking at is, okay, well, within a certain region, can I go through and find these limits there? So the region we're working with, the book just calls R lots of times, and that is a good name for it. Open region, closed region, hopefully we're kind of comfortable with those names. Open region is where we are approaching the boundaries but not equal to them, so like a dashed line on the outside. And then a closed region would be you can equal them, so like a solid line on the outside. And a few definitions, we won't really see these a whole lot, but just in case they come up there, we've mentioned them. So if we've got some region, it could be whatever shape you want. It doesn't just need to be a circle, it could be a square, it could be a blob, whatever. If we have an interior point, so going back to this idea right here, okay, an interior point means that for any point here, there exists, it doesn't mean that all of them are, but there exists a delta neighborhood, so a little circle around this, where every point is inside of this region here. And so if you're talking about an interior point like I have drawn here, that makes sense. You can just draw a little circle around it, it's totally enclosed. But if you're talking about something that is on the end, like this, if I try to draw a circle around this, no matter how small I make that radius, if it is on that endpoint, there's going to be parts of it that are outside. So this is a little section not in the region. Okay, so it's hopefully fairly obvious what they mean by interior, exterior. The way it's explained can kind of be a little weird, but if you can draw any circle around your point where it's a circle is totally enclosed in your region, it's an interior point, and then if you draw something where part of it is outside, that would be a boundary point. Okay, so we've got this guy over here is an interior point, and this point over here would be a boundary point. Okay, so it is hopefully as the names fit it pretty well. Interior, inside, boundaries on the boundary there. Okay, and then that can kind of be used to further classify interior regions and exterior regions. So open and closed region. An open region means that every single point's a boundary point. Because if you think about having like a dashed line on the outside of this region here, you can always make your radius just like infinitely small. You're never going to be able to actually get outside of that boundary region. Just keep getting closer and closer and closer to it, but there's really no end. It doesn't actually end there. Whereas if you have a closed region, you're going to have those boundary points, and the region, and all those boundary points are closed within it too there. So we're not going to see those terms a whole lot, but just if it mentions interior and boundary points, they pretty much are what they sound like. Okay, there's no real tricky definition to them. Okay, so let's talk a little more about the formal definition here. Okay. So there is our formal definition of a limit from Calc 1. So Chapter 1, Calc 1, just copied it from that part of the book there. So let f be a function defined over interval containing c, and let L be a real number. And then that statement means that for each epsilon greater than 0, there exists a delta such that, and then all those things have to be true there. So hopefully you remember going back and doing these. You were told that here's a function, find a limit, verified limit is actually true, and then maybe you were told the value of delta or epsilon, or had to go back and find the value of epsilon there. But we're not really going to worry about going through and doing epsilon delta limits in the two-dimensional case. Hopefully you kind of remember them a little bit, but we are going to do one example three-dimensional case here. But a little visual of what we're looking at here. So if we draw a similar picture to what we had in that first page, we've got some function f of x. It is approaching some point c. And then when we approach that point c, we hit some point L. Okay, so a similar picture is just what a definition of this. Recall what epsilon and delta mean. So what delta is, okay, delta is in the x direction. So it's that little bit of room we're giving ourselves around C that's getting us close to that point there. So essentially we're going to go delta in that lower direction, and we're going to go that same distance in that upper direction. And so that makes this little region here, and usually it's moving really small. Okay, not as big as this is drawn to scale here. But it makes this little region about the point we're getting close to them. And then what we're trying to do with this proof is say, okay, well, I can find that delta value that satisfies any epsilon value. Okay, and so what epsilon does is it's a change in the y direction, but it's something pretty similar. So we're going to go epsilon in that lower direction. We're going to go epsilon in that upper direction. There. And those should relate back to some points over here. Okay, and so the goal is we're usually given this epsilon, or we can say for any epsilon. And then the goal of what we're trying to do is go back and find delta. It's kind of like the goal of doing epsilon delta proofs. And then going back and actually doing a whole proof, showing that you did that there.
But
Felt a little familiar?
I think she's not
I
defining.
know everyone really loves doing that part of Calc 1.
It's just defining something, but that's.
I don't know if this really is worth it, but here is a thing I was using to check and see if I had sound, not what I meant to pull up there. So here is a little Desmos game type thing that kind of illustrates that too. So let's take a look at it real quick here. So if we're just working with the function x squared, okay, we can see our parabola right there. We've got some x value, and I can move that x value along the curve here. So just picking some value of x, let that value of c that we're trying to approach, they just call it x star here. But if we're trying to approach some specific value of c, say we're trying to approach 2. I know if I just plug 2 into the function, 2 squared is 4, I'm going to get a 4 out. So that should be my limit there. So let's just go to 4 right here then. Okay? So that line in the middle, that line right here, match up. What the green and little purple stakes are showing us is they're saying, well, this is what epsilon, this is what delta represent here. Oops, sorry, I didn't do that. So the idea of epsilon is that change in the y direction. So we usually say for any value of epsilon, find the delta, or if we're giving a specific value for epsilon, we go through and find the delta. And so it's just talking about that change we're traveling from the y. And then the delta that we're trying to find is basically, well, let's make sure that that little range in the x direction fits within that epsilon direction. And I'll drag this a little more. Okay, so there, make my face happy. I need to make this bigger. I can't drag it nice enough. Okay. So that's kind of the goal of the epsilon delta limits is, okay, well, what is this delta, this x range have to be to make this whole thing true? So when we do this in 3 dimensions, or an x and a y, instead of just looking at delta going in that one direction left and right of our x, we have to look in this whole entire circle of delta values. So very similar idea. We've got some 3-dimensional shape that surface that we're working with. We've got some limit we're trying to show it's equal to, but instead of just looking at this little 2-way area around our point we're trying to get to, we have to look at this whole entire circle. So before we get to the actual math of it, let me, there it goes. Oh, I just closed it. Impatient. All right. So here is a 3-dimensional picture of what we're trying to deal with there. And then we'll get back to the notes and kind of draw on that. All right, I don't have a lot of freedom to change things on here, so we're kind of stuck with the picture it has. But this orange part is our surface. That's the actual function that we're working with here. And if I drag it, you can see, okay, it's a neat little interesting shape there. What these blue planes are on the top and the bottom, that's representing that idea of what epsilon is. So it's the change in the direction of that dependent variable, which is z in this case. And instead of just thinking about it as lines that kind of limit it, we know that we're in more variables. So we have kind of like a whole plane that limits us here. So we're trying to sandwich in on where the actual limit is for this. So we can increase that, and there won't see much change here. We can increase that and put them further apart. We can decrease that epsilon and make those things much closer together. But we're trying to close in on what the actual value for a limit is here. So again, we're going to see a really similar process. For either any value of epsilon, we want to go through and find this. Or if we're given a specific value of epsilon, we still want to go through and find this. But the this we're looking for this time is that green part there, that delta. So if that little point in the middle of this is what we're trying to approach, we're trying to say, okay, well, what does the radius of this cylinder have to be in order to make sure that that cylinder and those top and bottom curves are sandwiching in the point that I want. So I can't really change things too much here, but if you can imagine that, I don't know if I can even make it do it, but if you can imagine that these didn't catch that point on the curve, then that would be a miss. We have like a little sad face in the previous graph there. But we're trying to say, okay, what does the radius of this cylinder have to be to make sure this picture works, to make sure that that point we're interested in is sandwiched between those two values of epsilon. So hopefully that shows it a little better than this static image does, although this image really isn't too bad here. So here's our 3-dimensional or multivariate version of that same proof there, the same limit or definition. We're still talking with the limit as we approach a point. We have that same notation showing up right here that we had on that previous page. But now here's that fancy epsilon delta way we're going to go through and prove this. And if you remember the stuff from Calc 1 from up here, this looks very similar. We're saying, okay, if we know what the limit is, function minus limit has to be less than epsilon. So we're talking change in the z direction. What's that z direction change? And we know that whenever we establish that, we're going to be able to go back and find some delta. So our goal for this is still to be able to find delta. All right, that's still what we're going to try to do here with this given information. But again, you have that square root part because you're talking about this whole entire circle, not just from the left or from the right, but the whole entire circle there, so it's a bit more complicated. So there's a more static picture of what's going on here. There's your little delta neighborhood, your little disk of radius delta. The point we're trying to approach is x0 right in the middle of that. And then what we're hoping is this dot right here, this is the one that we're trying to show our limit is. Okay, so that's the point that we're showing our limit is equal to. And then we have these boundaries above it and below it, which this picture just has a disk cut in that range there. So if we have the wrong value of delta, then this point isn't going to be in that cylinder, and that's a problem. Okay? And we're trying to make sure that that happens. I would have to do questions, but I can't hear you guys, so hopefully it's making some sense still. Let's try a fairly simple one. We're not going to do a whole lot of proofs here. And if you like proofs, I apologize. I'm not a huge fan of doing these, but it is important to understand what's going on there. All right, so here's the situation. We want to verify the following. We are given that our function is this here. Okay, which remember I was saying z, but basically our function is just x. Okay, that's the function we're working with.
Always, it doesn't want
to think about it this way, that's fine.
We didn't understand nothing.
What is the graph of that surface going to, you guys can't answer me. The graph of that surface is going to look like a plane.
Yes, of course.
Specifically this plane here. So there's the graph of the surface, f of x, y equals x. It's just this nice little plane that kind of cuts through the center there. And we want to know, we want to go through and first of all verify that the limit as we approach that 0.50. So as we approach this 0.50, we want to show that the limit equals 5. And that's what that graph had shown on it. It had that point plotted on it too. All right, so if you see that little point A kind of on top there, that's rotating away from me. Stop rotating. I'm so sorry. This is probably so stressful to look at. All right, anyway, that little point A, hopefully you can kind of see it up there on the top of it. We're saying as we approach that, we want to make sure that the limit actually is equal to 5 there. Okay. Well, the simple way to do this is direct substitution to actually find the limit. If we weren't told that it was equal to 5 there, if we just go back and direct substitute, so it's equal to 5. But the point of this problem is to go back and show for sure that this is actually true there. So if we think about it this way, there's 3 things we're given here. I already listed one of them, but I'll list them again. We are told that f of x, y is equal to x. We're told the function. And that's part of what we need for the epsilon delta limit. We are also told that the limit is equal to 5. So we're told L. Okay? And we are also told that x0, y0, that point we're trying to approach, is the 0.50. So all this information is just given to us from that limit definition right there. Okay? There's no mention of what epsilon has to be, so we are doing this for any epsilon. So it's just going to be in terms of epsilon in the end. And remember, the goal of what we're trying to do, and we're just going to stop after we find delta, but our goal is to find delta. So we want to find a delta that satisfies those inequalities in that definition we had on the previous page there. So here is one way we can approach this problem. Hi there. I'm having class now. That's okay. All right, so we are going to go back and set up this piece and then try to make it look like this piece. Okay, if we can make that first inequality look like that second one, that should tell us what delta is. So here we go. We're going to say, okay, the absolute value of the function, which is just x. Sorry, I wrote 5 up there. That should not have been 5. It should have said x up here. So I wrote this wrong the first time. That should have said equal to x. So we're going to have the function, which is just x, minus its limit, which is 5. And that has to be less than epsilon. And then the goal is to take this, and like I said, we want to make this look like this other part of the square. So 0 is less than the square root of x minus 5 squared plus y minus 0 squared less than delta. That's kind of our goal. Okay, we want to be able to make this look like this.
Really bad deltas.
We won't be done until about 11. Okay. So I would like to ask for suggestions, but I can't hear you, and there's no one in the classroom with me today, which is really awkward. See, look, they're all gone. I am talking to an empty room.
You gotta be kidding me.
That's a nice classroom. Yeah, that's way better than ours.
Of course.
Which is also why people keep coming in. They don't see any students, and they don't realize class is happening here. So anyway, we're trying to do this to get it to look like that. Well, we need the square root. Okay, we need to have a square root there, and we kind of already have a similar piece. So here's that x minus 5, here's that x minus 5. So we need to get this thing squared, and I need to have a square root on here. So we're going to go through and manipulate this absolute value. Would you agree, and you can just nod and shake your heads if you do, I hope we all do, that the absolute value of x minus 5 is equal to this expression over here? Do you agree those are the same?
Sure.
Right, because if we take x minus 5 and square it and hit the square root, we know we're going to get a positive number out, which is what the absolute value does, and the square and the square root basically cancel out. So these two things are equivalent. They're going to give us the same answer every single time. And that makes it look a lot more like the end result we're trying to get there. Okay. Now we're still missing that y squared piece, so we're going to have to do something about that. And the something we're going to do about that is basically just add it on. So we're going to say, okay, well, that's true, this is equal to this, but if I add stuff to this square root, I know I'm going to increase the value of it. So no matter what, this square root we have right here is going to be less than, possibly equal to, depending on what y is, it's going to be less than or equal to this piece over here. X minus 5 squared plus something. And that something we're going to go ahead and put there as y squared because it works out well for us. But it's just basically something. No matter what I do, these two things, hopefully we can see those guys are equivalent. They're always going to be the same. And the idea is that if I add something to this, which I know that's going to be positive, I know it's going to increase the value, unless it's 0, I'm going to be larger than the previous square root, right? So there's not really like math we're doing, it's just kind of like ideas that we're going writing down in terms of math there. So hopefully that kind of makes sense. But that's really the last thing we have to worry about, because this now looks like what we need. Okay, so we've met that goal. We've taken that original absolute value, we've manipulated it to look like the other piece, and that's pretty much all we have left to do here. So the idea is we know that this first inequality is less than epsilon, right? So there's no real good way to write this. We know this guy is less than epsilon, which means we know that this guy, let's write epsilon not 3. We know that the next guy also has to be less than epsilon. But we know that this last one, which is still going to be probably less than epsilon, we know this guy is less than delta. And so really what we're going to go through and do here is we're just going to let delta equal epsilon. Okay, as long as delta is epsilon, the whole thing should still be true. We don't have any misses there. We're going to be able to make that all work out, and that's going to be the magical number that we go back and pick for this. Okay, if we had a specific value for epsilon, we know the exact value of delta, but in this case, just epsilon equals delta. Technically, that's not a proof. A proof would require going back and doing this, and then kind of reworking through it to show that if delta equals epsilon, then all this works out. I'm not going to go through and do that. It's not really going to benefit us in the long run. Hopefully, just kind of understand the general idea works. It's very similar to what we did with the one variable stuff there, but that's like the only time I'll ask you guys to do this. Okay. However, if you do go back and look at your Calc 1 notes, because I know you all just have those hiding somewhere, if you go back and look at the epsilon delta stuff, you'll see that in linear cases, this often happened there. Unless we had some kind of slope on our line, epsilon and delta were usually the same thing there. In cases where we had slope on our line, epsilon multiplied or divided by something equal to delta value. So a lot of similarities between the 2 variable case and the 3 variable case. Go back and look at it and dig into it as much as you want. But honestly, I'm not going to ask you guys to do anything harder than this, so don't worry about saying, okay, well, what if it's a parabola? How do we go through and do this? We're not going to mess with that. Okay. What we are going to mess with, though, is finding the limit. Okay, that's something that I want you guys to be able to do there. Again, I would ask if there's questions, but for some reason, technology is against me today, so I am sorry. Okay. So what we're going to go through and do is we're going to go through and find out what the limit is. So something like we have here in example 2 and 3 and 4 and 5. We're going to go through and answer those. If we can just do direct substitution, like we can in example 2, then we're done. Okay? We're not really going through and trying to say verify limit, but just find the limit. So if you can do direct substitution and that works, then we're just done there. So let's try that on this one. If we go back and plug all that stuff in, we have 5 times X in this case is going to be just 1 because that's the point we're trying to approach here. So 5 times 1 squared. Y in this problem is going to be 2, which I kind of scribbled over there so it's hard to see. So times 2 in the numerator. And then our denominator, we will again have x squared, but now plus y squared. Okay, so it is simply just plugging all those points in. We're getting closer and closer to this xy point, plug everything in there. So what do we get? 5 times 1 times 2 is 10 over 1 plus 4, so 10 over 5, or 2. And that's it. That's the limit. The limit equals 2. And if you visually think about this, we've got some surface. I won't go back and graph it, but we've got some surface by that 5x squared y over x squared plus y squared. We're saying as we get closer and closer to this point 1, 2 for x, we should be hopefully at this limit value of 2. And this is a relatively smooth surface unless we're at the point 0, 0. So this is a pretty smooth surface there. So we're just going to see just a point on the surface. Is really all this is right now. But the limit is just 2. No problems on that one. Okay. If we run into problems, we're getting determinate form. We're going to have to either go through and factor, or go through and rationalize, or use trig identities to rewrite the function here. And on example 5, I don't tell you no limit exists on that one in the notes, but if I ask you to do something like that where limit doesn't exist, I'm going to say, show the limit doesn't exist. So if we get to example 5, you'll see what I mean in just a minute. And I will come back to this in just a minute when we get to example 5. So it's a little out of order, but if you want to note example 5 up by that, we'll come back to that in a minute there. So let's do a couple more where they work. We just got to do a little bit of algebra to get there. Example 3. Evaluate the following. Okay, you guys are smart enough to know if you plug in all those zeros, you're going to get 0 over 0. So feel free to go through and do the work on that, or just take a look at it. But we get 0 over 0, which hopefully you recall is indeterminate form.
I'm so bad at indeterminate.
Because you basically can't tell what the answer is. Typically, 0 divided by any number is just 0. So we should get 0 on this. But any number divided by 0 is usually undefined, so we should get undefined. So we're getting two conflicting answers. We're getting these two general rules that kind of butt heads with each other, and so there's different ways to go about solving this. Just because you get indeterminate form does not mean the limit doesn't exist. Okay, there are some cases where that will be the answer, but that does not mean the limit doesn't exist there. If this was a simple thing to graph, I'd say plug the function into your calculator, which isn't too bad. But plug the function into your calculator and see if it looks like it's smooth. Do you see any jumps, any asymptotes, something like that? But that's kind of hard to tell with 2D or 3D functions so far. So just know that if you get indeterminate forms, don't just quit. Try some algebra. And a good thing to try doing from here is to try to factor it or rationalize. Wow. Those are two fairly easy algebraic methods that usually fix this problem, which we saw in Calc 1 too. So let's try that. Let's factor this guy. So we still have a limit as x, y approaches 0, 0. Haven't done anything with that yet. But I can factor this numerator. Again, I'd like to ask you guys, but I can't because I can't hear you. So hopefully we can all see this is the same thing as x minus y times x plus y in the numerator over x plus y.
Oh my goodness.
Right? The difference of two squares. So we can see that, yay, that problem point cancels out. So the denominator term cancels with that. We are now just left with the limit as xy approaches 0, 0 of x minus y. And so now if we go back and try direct substitution on that, we write down what we're left with first. Okay, now if we go back and try direct substitution, we can get an answer. And so our answer is 0. At that point, it basically just approaches the origin. Again, I can't ask for feedback, but hopefully you remember that in Calc 1 when this happened, you had like a hole in the graph. So if you think about when you're working with functions that you were able to go back and do this canceling with, you'd like maybe be able to cancel out that quadratic and rewrite the function as just a linear function. And the difference between the two equations was on the linear function it was smooth, on that quadratic function had a hole at that point that we're looking at. And that's basically the same things that happen here. You're going to have some smooth surface, so it looks like it's just nice and continuous there, but there's actually a hole at the origin. Okay, but that would be the limit. Limit just equals 0. All right, example 4. Okay, this is another one where you go back and try direct substitution and things don't work. You get indeterminate form. So we'll show that just to make sure that we're all clear on kind of the process I would use here. So if x is 1 and y is 3, then we're going to subtract 2. And then we have 1 plus 3 minus 4. So 1 and 3 is 4. Square root of 4 is 2. And then 1 plus 3 minus 4 is just 0. And then again, it's a determinant form. This is one where rationalize. It's not really anything to do to factor this since we have that square root there. Again, I'd rather ask you guys what to multiply by, but I can't. So I'll just tell you. Just rewrite the equation for now. Okay, so we're going to multiply by the conjugate of the square root part. So the square root of x plus y plus 2 over itself. Does that process look familiar?
Yeah.
And then just go through, simplify out, and that should, on these nice textbook problems, it should kind of cancel out that problem point, and and then we should be left with a solvable thing there. So we still have a limit. If I distribute across that numerator, those first two terms of square root cancels out, so I'm left with x plus y. Since it's the conjugate, the middle terms both cancel, so I'm not going to bother writing them, but -2 times +2 is -4. And then the denominator, I'm not going to bother distributing because that first expression is what's going to cancel there. So all of this cancels all of this. So we're left with 1 over that part we introduced, and we can go back and use direct substitution. So here's what we're left with. And if I go back and plug everything in, we get 1 over the square root of 1 plus 3 plus 2. So 1/4. And aside from having x and y, this should look very familiar to stuff from Calc 1. I know it's been a long time since you did it, but it's the same processes. Okay, just because you get 0 over 0, don't quit. Try to rationalize, try to factor. I don't have an example of trig here, but you can go back and do trig identities, and sometimes that helps too. Okay. Seem okay so far still? I left, so I'm assuming that's okay. All right, this is one where I'm kind of tricky in the wording here. Say evaluate the limit, but I'll tell you now, the limit does not exist. So a better direction on this one would be show limit does not exist. Okay, and on a quiz or a test, that's how I would word it. So I should have been a little more clear here in the notes there. But we can start off the same way. If I go back and use direct substitution, you're going to see you're going to get 0 over 0, which is in determinant form. But there's nothing you can do to factor this one. There's nothing you can do to rationalize this one. If you were to go back and look at a graph, it kind of gets funky, so I don't think that's going to help here, but it's not going to make it any easier to see what's happening here. In cases where we're trying to show the limit doesn't exist, when we're working like with a two-variable function, just like an x and y there, the process is a little different than what we're doing now. So what we're going to go back and do for this, if I flip back to page 9 for a minute here, okay, we're essentially going to go through and find two paths to the point that don't bring us to the same location. So, for example, and this, I don't know if this is a really good example, but if you take one way to get to that point x, and you take a different way to get to that point x, y, maybe one takes you to a z value of 1 and one takes you to a z value of 10. You're going to the same x, y point, but you're ending off at different heights. It's kind of like our graphs, and they have like a jump in those graphs. If you approach it from the left and approach it from the right, it gets to different points there. It's essentially the same thing we're looking at here, is when I approach these points from different ways, different directions, I'm getting to different locations.
You couldn't even ask enough.
All right,
Sometimes these are much easier than other times. But again, showing limit doesn't exist. We're trying to show
I don't think he can answer you.
that two paths. In this case, the point is 0, 0. So if we take two different paths to that point 0, 0, lead us to different function values.
I don't know, bro. I don't know.
Okay, or different values of z. If we can show that, then we show the limit doesn't exist. Because every single thing in this little delta neighborhood has to take us to that same point, has to take us to that same z value. If we find two that are different, we know we're not continuous. We know the limit doesn't exist at that point. So I will just tell you some good ones to try using. Make this as simple as you can. There's an infinite amount of paths you can take that'll traverse this point 0, 0. But a simple one is get on the x-axis and get closer to 0, 0. Okay, so you keep your y value just the same at 0, and you just make your x, say, like smaller and smaller and smaller. If you're going from x is 3 to x is 2 to x is 1 to x to half. If we just think about traveling along that x-axis, if we get closer and closer to the origin for the point 0, 0, that's going to be one of our paths. And then another easy one to do is do the same thing along the y-axis there. So in the case of working with 3 dimensions like this, the point we're trying to get to is here at the origin as x0, y0, and we don't know what the height is right now, but that's the kind of delta neighborhood we're looking at here, is going around this point here. So one of the paths we're going to look at is say, okay, if I get closer and closer to this point along the x-axis, okay, where does that take me? What z value does that end me at? And if we say, okay, well, let's get closer and closer to that point along the y-axis, what z value does that bring me to? If they bring me to the same ones, then I gotta try different paths. But if they bring me to different ones, then I'm done. Okay, and you can go the negative direction, positive direction. You can go along the line y equals x or something like that there. But these are two fairly simple ones. Since you're working with zeros, one value's not changing, we can go back and plug in. So let's try that. So let's say the first one we're going to look at is along the x-axis to the point 0, 0. Okay, which means that what's going to be happening there is the x value is going to be changing, but we're going to fix our y value to be 0. We're going to allow x to be different values, and the limit's going to get smaller and smaller and smaller and closer to 0 there, but the y value is always going to be 0. So if we go back up to our function and plug that stuff in there, so we're saying as xy is going to approach, yeah, we'll still write it this way. Let's approach point 0, 0, but now we're going to have x over x minus 0. Because we're basically going back and saying, okay, well, if we force y to always be 0, what happens here? So you can simplify that pretty easily. Minus 0 doesn't change anything. X over itself is just equal to 1, so we get to 1. So if I'm traveling along this path here, I'm going to end up at a z value of 1. That's where this path takes me. It's that point right there. Okay. So let's see what happens if I go along the y-axis. So we're going to do the same thing. So along the y-axis to the point 0, 0, which means now we're keeping x fixed because we're on the y-axis. We're not going anywhere left and right, but we're going to allow that y value to change. So do the same thing. We still have a limit as x, y approaches 0, 0. But now x is going to be 0. Y we're going to leave there. Okay, because again, the idea is we force that to always be 0 and kind of see what happens, what's the change. And in this case, we get 0 over negative y, which no matter what is always just 0. 0 divided by anything is always going to give you 0, so we get 0. So the point that this blue path takes me to is indeed that dot right there, which is not the same. And so that's sufficient right there. So we can say since 1 does not equal 0, we know we are at different locations. We have two different, we'll say, values of z. So the limit does not exist. Okay, there's a jump in the graph at that point. We found two paths in this delta neighborhood that take us to different locations. We don't have a continuous function at that point. There's like a non-removable discontinuity. There's nothing we could do to fix that. Can't factor, can't rationalize, can't do something else there. You're just kind of stuck with this thing here. Okay. So that's, like I said, those two paths along the x-axis and along the y-axis are good kind of default ones to start with because they're fairly easy to control the changes in. You fix one variable to be 0 and kind of travel on that path there. If you were going to a different point, so say you were going like to the point 1, 2, or something like that, then I would say, okay, well, we can do a similar idea. If we were to go along the line x equals 1, well, similar thing there. We go back and say, okay, well, if x is always equal to 1 and y equals something that can change, we can still go back and do the substitution and vice versa there. So whenever you're asked to go through and show if the limit does not exist as you approach a specific point, I would do something very similar. Let's take a vertical line, or not really vertical, to take two perpendicular lines, one that travels in the x direction, one in the y direction to get to that path there, and just see what happens. Most of the time, that's going to be able to be enough to show what's going on there for our textbook problems. Okay.